welcome to the LDE Center for Sustainability Circular Industry Talks, already the first one of this year in the first few days of the year. I'm glad to introduce today's presenter, Hazem ELTohamy. Hazem is a PhD candidate at the Institute of Environmental Studies of Leiden University, and he is carrying out his research in the Transcensus LCA project and will discuss life cycle assessment practices focusing on the electric mobility sector and addressing the state of life cycle assessments for electric vehicles and potential for harmonization that could ease comparability and support decision making. Hazem, please go ahead.
Thank you so much, Ruud, and at least for the invitation. It was really nice of you. And let me dive into it. All right, let me start first by a few information about me. I had my bachelor degree in civil engineering back home in Egypt. And then I did my master's degree in environmental engineering. I started developing this interest while I was home about the environmental issues and how I can contribute to sustainability efforts. So I went to Italy to do my master's in environmental engineering and specialize in that. And I did my master thesis in life cycle assessment. Of course, during my environmental engineering program, I got introduced to the life cycle assessment, and I really liked it. I really liked the concept of it, and I chose to use it in my master thesis. And I had a collaboration with the Red Cross organization, the ICRC, to apply LCA for their waste from automotive lubricating oils. Regarding my previous roles, I worked as an environmental engineering consultant for 1 year, and then a quality control engineer in the construction sector for 2 years. And then I decided to dedicate myself to research, where I started my career after my master's as a research assistant in Politecnico di Milano in Italy, and also as a teaching assistant of LCA. So I can say that the fields of expertise is mainly now life cycle assessment. I've been working with LCA for more than 4 years now. And from technological point of view, I focus on environmental and waste management systems. Current role, as was introduced by Ruud, as a PhD candidate at CML, Leiden University, and my research theme now is about LCA applications for zero emission vehicles or electric mobility, although the terms are a bit debatable, but yeah, this is my research theme now, and I'm supervised by amazing supervision team, including Jeroen Guinee and Bernard Stoibing and Rupert Sestrade, who is in this room, by the way, today. For those who are not really familiar with LCA, I would just say a couple of words about it, just to get everyone on the same page. LCA is a standardized quantitative method to evaluate the potential environmental impacts of systems over their entire life cycle. When I say systems, I mean products or services. Life cycle thinking appeared as the counterpart of end of pipe thinking, where in life cycle thinking we think more of the entire life cycle of systems, from raw material extraction until the end of life, considering disposal and possibility of recycling. And within this life cycle, we exchange a lot of emissions and materials with our world, where we try to quantify in our models and link this to environmental impacts. While end of life thinking, I think the photo is very expressive. We just think on what's coming out of the stack or the exhaust. LCA is standardized in ISO in 14004, 14044, 14047, and it is the basic for many famous guidelines like the PEF, or Product Environmental Footprint, by the European Commission, the Greenhouse Protocol Scope 3, which is based on also the life cycle thinking, ILCD handbook, and a lot of other guidelines. In a nutshell, the framework of LCA consists of 4 iterative phases, and I'm sure people who work with LCA are very familiar with this graph here, with this figure from ISO. Goal and scope definition is the first one, where we plan the study, we set the scene, as we say. We take some decisions about where the system boundary is, what our function unit is, and the purpose of our study, and many other decisions. And then we move to the data part, which is the inventory analysis, where we quantify the inputs and outputs of our system in terms of emissions and material used. Then we quantify the environmental impacts, or calculate the environmental impacts, in the impact assessment phase. And finally, we interpret the numbers we get by understanding what they mean and how they can lead us to meaningful conclusions. Now let me move to the topic that we're going to talk about, which is road transportation and electric vehicles. Road transportation is one of the main contributors to many environmental problems that we are encountering nowadays. Of course, on top of the list, I cannot omit that, is climate change, certainly. In this small pie chart here, you can see the transport contribution compared to other sectors. I'm talking only about direct contribution. In 2019, you can see that the transportation as a whole contributes to with 15% to the entire the global GHG emissions in 2019. After the big three, which is the industry, the power generation in the forms of electricity and heat, and agriculture, including forestry and livestock, as we know. And you can see that the road transportation on its own contributes to 10% of this entire 15%. So you can think of this 5% of aviation, maritime, and the other means of transportation. So you can understand how road transportation is quite crucial in this big equation. In the EU, now we are moving to Europe. Transportation contributes to about a quarter of the EU's greenhouse gases, and 3/4 of this comes from road transportation. Therefore, electrification appears to be one of the most prominent strategies for decarbonizing road transportation in order to mitigate this big impact. And it is gaining a lot of momentum nowadays. You can see the market of the EVs increasing, especially in the EU and countries like China and the US. And in the EU here, a lot of bodies like the EU Sustainability and Smart Mobility Strategy, they advocate for an irreversible transition to zero-emission mobility. So, despite this these ambitions, there is a big problem of burden shifting that can happen due to rush decisions when it comes to moving to full electrified mobility. And here the LCA role can appear, and it can play a pivotal role in guiding these transitions without, or at least mitigating the burden shifting risks that can arise. We don't want to solve the climate change problem by causing another problem. This is basically the burden shifting risk. Now let me move to the project that I'm working on. It is called Consensus LCA, and it's a Horizon EU project. What is it about? LCA, Transcensus LCA is an initiative by the European Commission to harmonize how LCA is applied in the zero emission vehicle sector and the traction batteries within Europe. Why is this? Why is this important? If you read the LCAs done in these fields, and there are many LCAs done in this field, you realize that it's very diverse when it comes to methodological choices, when it comes to data assumptions and certain decisions that the practitioner has to take. So the subjectivity in these choices can hamper comparability and also transparency when communicating this to end users. Also, it's not really helpful to policy making because it can have a huge impact on the conclusions of the studies. Who is working on this? In Transcensus, we have a consortium, very diverse consortium composed of a wide spectrum of stakeholders within the sector. In Europe, of course, since it's a European project, it's mainly European beneficiaries and partners. So we have people from industry, the big automotive manufacturers, from research, including ourselves at Leiden, and consultancies, and also, of course, the EC is involved as the policymaker. So what is the roadmap of the project? What do we intend from this project? We started from literature review, which will be our talk today, and then from the practices that are available already in literature, and by analyzing these practices, we think what would be the best and the most practical and scientifically robust way to go. And this takes us to the second step, is agreeing on this specific choices that we determine and build consensus on these choices. Then we gotta test these choices, and we are actually in this phase now. And hopefully we can go from this point to standardization after we verify that the method is working and it satisfies the criteria that is intended from it. And of course, outreach. We want people to use this method eventually. So yeah, this will be our last step in this journey. I'm not gonna go through that. It's just some of the project beneficiaries. We have also like advisory boards that include more people. And this is the project website if you want to know more about the project. Now let's dive into the topic of today, which is the literature review, the topic of the article. Just few information about what we did here. An important step towards harmonizing these practices. We thought it should be reviewing what's there already and analyzing the state of the art practices in the EV LCA application, just to understand where we're starting from. And I highlighted here the word practices because in this review we did not review results or made a kind of quantification of what the studies conclude or something like that, as a typical review would do. We focus more here on what's behind the scenes. What did the practitioner do or choose in order to achieve these results? In this work, we reviewed various types of sources that can be categorized in sectorial and generic guidelines and standards, studies from academia, original equipment manufacturer OEM studies. And when I say OEM from now on, it means the car manufacturers, just to be clear. And the life cycle inventory databases, of course, which is a very important pillar in life cycle assessment. And our purpose was to identify the key methodological approaches and data selection, and perhaps highlight where problems can lie when it comes to harmonization, and certain practices from what we reviewed that we think could serve as starting points for harmonization in the next step. What is the review scope? I thought this is important to mention because when you go and read the LCA in the EV sector, you will, or automotive sector in general, you will realize that there are many types of LCAs applied there. Of course, we needed to make a choice due to the resources available that we could invest in this work. So we ended up with 3 archetypes that we could conclude from our from the expertise in the project, which are the LCA of existing products, prospective LCA, and fleet level LCA. Just a few words about each. LCA of existing products is about the products that are mature and already available in the market. And the prospective LCA is usually employed to study a project that is not that have a low technological readiness level or in the development process, but it's not deployed fully in the market on the market. And this is usually used to test new components or new technologies. And then there is, on a bigger scale, on a system or economic scale, we have what's called fleet level LCAs, which is more about building policies on a national level or the company level when it comes to the mobility services. In our work here, we focus mainly on the first one, since it is the mostly used and employed, and what people care about mostly now and apply in their studies. However, we touched upon the 2 archetypes in another work, and you can see it here if you are interested. Regarding the topics analyzed, we choose certain topics that we thought that are very important and contain a lot of controversy among the studies, and this is what we're going to discuss. Now let's jump into the results. However, just a quick disclaimer here. Of course, I couldn't get into all the details. It's a big article and contains a lot of information and details. So I just tried to get the summary of it in a very abstract way. And of course, I'm open to any questions that we can have at the end of this presentation. I will start now with what concerns the goal and scope mainly, the first phase that we talked about. I will start by the system boundary, and I make here some distinction between vehicles and batteries. In most cases, this is usually not necessary, but in some cases it's quite necessary because the practices can be quite different depending on the product you are evaluating. So when it comes to system boundary, we realize that the cradle to grave type of system boundary for vehicle is the most prominent. So most of the studies that we saw apply a full system from cradle to grave, from raw material acquisition until the end of life. It is the same for batteries. However, there is a very important topic on batteries which relates to production. Hence, you see something like cradle to grave, which is mainly concerned about the production of batteries. Then we move to another important topic, which is the function unit. And here, the most common when it comes to vehicle is what we call distance-based function units. This can be expressed in many units as vehicle kilometer, passenger kilometer, or ton kilometer. it's mostly dependent on the type of transportation. We're talking about passenger transportation or freight transportation, goods, in other words. For batteries, you can see a bit of a variety there. However, the distance-based kilometer, of course, we are talking about traction batteries here, just not to get confused, as the batteries used for car propulsion. So we have the distance-based still. It's, again, the most used one, also in case of batteries. Capacity-based, throughout-based, and based and mass-based. The capacity-based is it's basically you can think of it as how much energy can the battery can store. So it can be expressed in 1 kilometer or 1 megajoule of battery storage capacity. The throughout is more on the what this battery can give. So usually expressed as 1 kilowatt hour of the total energy provided over the service life of the battery. And then you have the last one, mass-based, and this is more for the cradle to gate, where you get more of the mass of the battery produced. And this is used, for example, to compare cathode materials or battery technologies in the production phase. When it comes to the cutoff rules, cutoff means exclusion. We saw that this exclusion usually took place based on mass, energy, or environmental significance of flows and processes. These are the three most used criteria or three only criteria that actually people use in deciding their cutoff. And in terms of activity, we noticed that maintenance and infrastructure, when it comes to vehicles and batteries, are the most overlooked one. Although this is not usually acceptable, but this is the current practices. In our work, we provided, as I said, certain starting point for harmonization, and one of this regarding these topics is the recommendation of cradle to grave or cradle to cradle, in the sense of circular economy. So this means recycling or reuse, or whatever strategy in that sense, because this is the accurate translation of full life cycle, either of a vehicle and a battery. Otherwise, the concept of life cycle thinking is a bit not complete. And cutoff, as long as the resources allow, we believe the cutoff should be avoided. Everything should be included in LCA. However, we understand that this cannot be practical all the time. So we suggest what is called screening studies, and this is also recommended by PEF, where you can get in a quite quick manner what can be included and when what can be excluded. Sorry, and what is not really impactful on the results. And we also push towards the distance-based function unit, as we believe that's best reflect the intended function, either for cars or batteries, which is transporting people or goods over a distance, basically. We can skip this. This slide is just about what are the terms used in the EVs when it comes to system boundary, and this is only specific when it comes to fuel provision, but it's not really important to our presentation today, but it's just for information. A very important, a primary challenge in that we noticed in deciding the distance-based function unit is what's called the lifetime mileage, or the lifetime of vehicles. This is crucial because this dictates how impacts are distributed over every kilometer driven. So you get the results basically per kilometers at the end. So this can have a huge impact on this. And also the significance of the use phase, or what we call well to wheel. Well to wheel is the use phase of the vehicle, basically, and this can influence the impact distribution between the production and use stage. If we don't get that right, we cannot really take the right decisions. So this is why this decision is very important on the lifetime of vehicles when you decide the function. And you can see here the variation that we noticed. For example, in the heavy-duty vehicles, it can go beyond 1 million kilometer difference. So this is something that we also think that we have to pay more attention to. Now I'm gonna move to data. Just a couple of things that we noticed here. We noticed the lack of standardized approach to inventory data collection. We also noticed that the data quality and availability varies a lot according to life stage. So not all life stages are represented by the same quality of data. And lack of primary data, especially in raw material acquisition end of life, is very evident, especially when the OEMs or the companies do the LCAs. Apart from energy consumption, which is, of course, energy consumption of vehicles and batteries, whether in use or production phase, is the prominent element in the use phase, but the elements considered in the use phase differ significantly between studies. And we also, this is very specific to industry, that they have their own platforms where they exchange data with their suppliers, component suppliers, and then they link that to the LCI databases to model their vehicles. I will get to that in the next slides with more detail. What we recommended here is data traceability systems. We think that such systematic systems like the IMDS can actually help a lot create a better network for primary data sharing. And this is very crucial, especially for the weak rings in the cycle, which, as I said, the raw material acquisition and the end of life. We also saw that a lot of secondary data used from databases are quite outdated in the studies that we encountered. So this is very important to be updated because the world is moving so fast, especially when it comes to EV and battery technologies. The priority should be given to the most impactful activities when it comes to a higher share of primary data that should be included in studies. This is the typical information flow for OEMs when they model their vehicles. Just these arrows represent, it does not represent material, it represents information flow. So usually the companies, the car manufacturer, you can think of, I don't know, DAF in the Netherlands, for example, or Renault in France. They usually get their components from external suppliers. However, they have this thing called International Material Data System where they share information with their suppliers, and the suppliers can give them more information about the components that they are providing them with. And this IMDS can give information about the material compositions of these components. And then the OEM can use this in complying what's called bill of materials, where you have a list of all materials used in the car. This is to be complemented by the in-house supply of components, because sometimes some car manufacturers manufacture some of their own components. And then this can be grouped into material groups from the BOM, and then material groups can be assigned to production processes to obtain these materials. And then the amount of material groups and processing needed is decided, and then the linking happen in the LCA data, LCA software between these groups and the processes in data in secondary data sets usually. And then this feeds the LCA model along with the in-house activity data, which is basically the energy consumed and the energy consumed in the manufacturing process within the premise of the vehicle manufacturer. And then you end up with the LCA model. Now to a very important topic, which is electricity modeling. And this topic can be summarized in two main arguments that we found in the reviewed work. First argument is location versus market-based modeling. And the second one is the static versus dynamic modeling. And there is a huge debate about this in the field that we also encountered during the project discussions between the different partners. What are we talking about here? The problem here is that we saw that the problem is of double counting is a staple in all the work that we encountered. It is a problem that is discussed in the literature, but unfortunately, it's not really taken into account much when applied in real studies. We also realized that a lot of studies use what's called the static modeling when it comes to how the electricity feeds the entire life of a vehicle that extend to many years. Now, let me just a few words about what I mean by location-based and market-based, because I know some of you might not be very familiar with this. The location-based modeling is based on the regional consumption mix, basically. So you have your grid that consists of coal, natural gas, and parts renewables, and you get an average over a specific year or region, talking about the country or region like the EU27, for example, and you just use this in your model as an average mix as the electricity source for your manufacturing. Unlike market-based modeling, which gives you more control on what the kind of energy you use, and this is done via what's called EACs, which is energy attribute certificates, and it is exclusively claimed energy sources that are bought by the car manufacturer, and it's usually from renewable energy to improve the environmental performance. And then this is used in the model, and the rest that's not covered by certificates is provided what's called residual mix, which is basically the grid mix, so minus the all exclusively claimed renewable energy, and then you get the sum to feed your system or your manufacturing process. What is the problem here exactly? What is the problem of double counting? The thing is that we noticed that it's quite common to do what's called parallel application of both location and market-based modeling in the same model. We divided these problems into three levels. We saw that this problem can happen on three different levels. The two level 2 and level 3 are typical cases of parallel application. So level 2 is when within the OEM system itself, so it's in the manufacturing phase of the life cycle, you see that the parts of the car is actually modeled using average mixes, which is location based, basically. That is fed. That is how the databases, secondary databases like Econvent or Gabi is constructed, and then of course this resonates into the other. Feeding into other data sets, like for the battery, for example. However, then you have the OEM part where they have more control over the manufacturing process. For example, think about the car body, where they use the market-based. Hence, you can see the double application here. Another level is when it happens on a bigger scale, on the life cycle of a car. So in the raw material acquisition or OEM production, and then in the use phase and the end of life, think of here of the end of life or recycler or something that use the market based on certificates and residual mixes. However, everything that is modeled in the production and the raw material acquisition is done by the location based. So these are typical cases of parallel application, and this leads certainly to double counting. Level 1 is another level where double counting can happen, which can occurs within each method. So in location-based, for example, if a specific kilowatt hours are consumed by a certain time, think of hourly resolved, so per hour, and geography, think, for example, of Eastern Europe, are accounted for by a certain factory, and this same kilowatt hours are also part of the average mix. So, for example, annual resolve for entire Europe. So these kilowatt hours are double counted due to the overlap, geographical and temporal overlap. In market-based, however, the double counting can occur due to how guidelines provide recommendations apply to this application. So this usually provided in a hierarchical way. So do this if you cannot do this, if you cannot do this. So just an example, if a supplier specific total electricity mix, supplier here means supplier of certificates that gives you renewable energy. So it comes after supplier specific electricity products in this hierarchy, which recommends, okay, go for this certificates first. Is calculated according to this the same method at the country specific total supplier mix. This would contain exclusively claimed electricity products, hence, again, double counting. So this is a big problem and can lead to a lot of misconclusions, let's say. So despite being crucial in a vehicle life cycle, electricity modeling harmonization is a very tough challenge that we encountered, and we are still working on that in our method development because it's really hard to agree on one thing. Although it's very hard to claim that one is better than the others. However, we think that the location-based method can easily be harmonized to minimize the double counting risk. However, if we disregard market-based altogether, this might seem unfair to companies who try to really invest in better energy and cleaner energy. So yeah, it's a bit controversial. Now I move to the second topic, which is the static versus dynamic modeling. This is a bit simpler. It's about how you account for the grid evolution, for example, to be specific. And this is mainly concerning the location-based. Again, it's more about the specific geography, where you just use the average consumption mix in your model. So static modeling just basically assumes that the same grid mix will be the same, feeding the entire life of a vehicle that can extend over 15 years. However, the dynamic modeling accounts for the ongoing evolution of the grid mix towards decarbonization. Obviously, we cannot deny that in the last decades the grid developed a lot towards decarbonization, having more renewables, and you can see here that in the EU 27, the portion of wind and solar energy has increased a lot in the last decade. Therefore, we think that it's very important to take dynamic modeling as the basic for any harmonization effort, because it gives a more realistic picture of the use phase of vehicles compared to just relying on what we have now as present mix, and that can lead to unrealistic and more pessimistic results of electric vehicles in the future. And this is also taken and adopted by policies and guidelines, directives. I mean, like the EU Renewable Energy Directive, car and van CO2 regulation, that talks about the same recommendation. Another topic is multifunctionality. Multifunctionality is about having multiple functions for the single system. This can happen on many levels, but we found that in LCA studies, people usually distinct between the end of life and upstream processes and the multifunctionality that can happen on these two parts of the life cycle of vehicles, which is a bit strange to us. studies and are relatively vague when defining and dealing with multifunctionality. So it is quite strange when you see allocation applied without even determining the problem, that there was a multifunctionality problem and allocation had to be done. So this was also common. We also noticed that in the upstream processes, upstream to EU, the end of life for the vehicle life cycle and batteries life cycle, there is a mixture of partitioning, which is the allocation, and substitution. These are the two main concepts to solve multifunctionality problems. A mixture of these is used in the upstream process during the end of life. And in general, for the end of life phase, where you can find things like recycling or energy recovery, and these are quite typical multifunctionality problems, where you have the function of disposal disposal, and you get a product also out of it. We found 5 choices in the end of life, which is the circular footprint formula from the PEF, the cutoff approach, substitution, the 50-50, which is a certain kind of allocation based on 50% percentage, and allocation at the point of substitution. However, this last one is more applied in the EcoInvent database, and it's not really considered in studies much. The 2 most common ones, though, are the cutoff and the avoided burden. Avoided burden is just another name of substitution, where you get negative impacts or credits for when you recycle or you recover energy. There are more to say about this. It's a huge debate in literature. So please refer to the full article if you want to know more about it. And this is also very debatable topic, multifunctionality, and it's a challenge to harmonization, because there is actually no correct solution. It's rather a perspective. Well, ideally, dealing with multifunctionality should follow a consistent method that we didn't find in the reviewed literature within the single product system, at least, as well as across different product systems, because this is an overarching problem. It's not only EV sector related, because this material, when it comes to recycling, for example, material feeds other sectors that use different rules. So this require more global harmonization, let's say. However, we understand that this is quite far-fetched and hard, and it's not feasible in practice, because, people see that some approaches are more suited to particular multifunctional processes, or there are predefined choices in databases that people cannot really change. Think of example of the EcoInvent, the cutoff allocation type of database, database that, you don't have much to do about this, or there are conflicts between sector guidelines. For example, the steel manufacturer that feeds the car manufacturer, they have different governing policies and different governing guidelines. So this can conflict when it comes to how to solve this multifunctionality problems in models. However, we believe that at least the approach to defining the problem should be harmonized, and we provided some recommendations regarding this in our paper. However, solving the problem altogether is not yet there. I'm coming to the end now. Now we have the life cycle impact assessment. If you remember, this concerns the 3rd step of LCA, or the 3rd phase of LCA. We saw that the most common methods employed are the recipe and CML-IA. These are the most used ones in the work that we reviewed, and we also noticed this mixing of impact indicator from different methods, and this is a common practice, because in some work this is justified by one method being better in a specific impact category than the other when it comes to the more robust characterization model behind it to obtain the results. When it comes to the reporting of results, the climate change, acidification, photochemical ozone formation, and eutrophication are the most reported in the work reviewed. However, we noticed some odd things as well, that the abiotic resource depletion and particulate matter formation these impact categories receive little attention, despite being quite relevant to the field, especially when it comes to raw material consumption in the sense of abiotic resource depletion, and also the particulate matter when you compare a conventional vehicle with an electric vehicle. In our work, we suggested to follow the EF method by the European Commission as a starting point, since it's the most comprehensive and also continuously updated, since it is managed by the EC, and also provide other options when it comes to normalization and weighting, and it's quite well documented. We also recommended adding other indicators like on the LCI, or the life cycle inventory level, which is the cumulative energy demand, and this is very important when it comes to evaluation of system efficiency. And this stems from the fact that improving the system efficiency is very important in meeting climate change objectives, and it's a central pillar in the entire EU overall climate and energy framework now, especially when you consider the competition between sectors over renewable energy. The last part is on uncertainty, sensitivity, and scenario analysis. Here we redivide again between vehicles and batteries. We noticed that the uncertainty propagation, which is usually done in the uncertainty analysis, is quite seldom in the work done. Instead, this is kept directly to one at a time sensitivity analysis, which is basically just testing the change of one parameter in the model and just see how this affects the results, without really working with statistical data about the propagation of the uncertainty. What are the most common tested topics? Energy first. The use says consumption. How much energy that the vehicle use in its use phase, and also varying the electricity grid mix based on the geography where the vehicle will be used, and the mileage. Just remember here what we talked about in the lifetime mileage and how it varies. So this is also one of the things that people test in their studies, because there is no big agreement on it. For batteries, the battery components are one of the things that are tested. So how changing certain components can affect the results of the battery, and also the recycling rate in the end of life of batteries. Uncertainty and sensitivity analysis are vital in LCA, and we believe that a sweet spot has to be found between resource efficiency when it comes to time and money, because we know that's computationally not easy, especially if we go to the sophisticated methods. But we need to find this balance between the sophistication and also the knowledge of the LCA practitioner when it comes to math and statistics. We believe that, again, similar to multifunctionality, the uncertainty in LCA has to be done in a more structured way. It doesn't have to be very complex, but it has to be structured. And literature, luckily in that regard, provides a lot of guidance in that sense. I think this is our last slide here, and it's basically on harmonization. We thought about also the idea of harmonization and how this can be benefit and perhaps not benefit the LCA community in the EV sector. As I said, harmonization is necessary for comparability, transparency, and consistency. to have more confident policy making and fair market competition between in the industry. The successful method should be scientifically robust, of course, but it also has to account for a lot of concerns and limitations of various stakeholders. And this is something we realized during the journey of this project that has been going on now for 2 years, that people think very differently depending on the background they come from. So this balance has to happen in order to have a widely adopted and accepted method. If this is our final target, hopefully. There is one thing that also worth mentioning here, that there is an opinion that harmonization is not good all the time. Because especially when you think about it as an academic, this way of thinking can really stifle any innovation or better choices or suboptimal choices in specific cases where you need to think of in certain cases, and instead of just following very strict guidelines. So yeah, it's a must, but at the same time, it has to be looked at with a bit of caution, that it does not hamper any innovation efforts in an improvement in the application of LCA. That's it from my side. And if you really want to know more, you have the full article is here, and our consensus method will be available this year publicly, and you can follow it on this page here. And that's it. Thank you.
Thank you, Hazem, for your introduction in this quite complicated topic. We don't have that much time left for questions, but who may I give the floor for a question to Hazem? Otherwise, I would like to start myself with a question. And
Peter has a question.
Peter, I first go to Peter.
I cannot hear.
We don't hear you, Peter.
Oh, no.
Yes.
But we lost you completely, I think.
Okay, then I will ask my question, and we'll see if Peter jumps in again. You discuss harmonization in the context of electric vehicles.
Yes.
But next to electric vehicles, there's also publications that compare electric vehicles with fuel cell or hydrogen vehicles, or that compare electric or cars in general with planes, trains. If you look into harmonization, you would also like to take those into account. Would it become far more complicated, or is it something that you basically already have prepared by looking into harmonization of electric vehicles?
Well, this is a very good question, and it relates a lot to what I have discussed here about the different interests of stakeholders and the different sectorial guidelines that governs these sectors. It is very hard to lump sum all these industries that all come under the umbrella of mobility in one shot for harmonization. I think this is a very complicated task. I think at certain point this should happen, and not only for between the different means of transportation, but it's again about other sectors that serve this complex kind of industry, because you see whatever we decide here can directly conflict with other decisions made perhaps in another initiatives to harmonize the steel manufacturing. So
okay, yeah, so yeah. Quite clear. It gets far more complicated even. I see in the meantime that Peter has returned to the meeting. So Peter, please go ahead.
Yes, I pushed the wrong button. Sorry. Yes, thanks for the methodological talk. I was looking for some numbers, and probably you have also encountered numbers and insights during your study. And I'd like to ask what are the most remarkable things that you went into during this research from insights in this subject?
I think, do you mean numbers in the sense of LCA results or what?
Yes, yeah. I heard sometime that an electric vehicle should make 80,000 kilometers before it breaks even. So
Well,
things like that. So I was wondering where you went into during your research that you think that's remarkable to share.
Yeah. As I have given the background here, our work here was a bit different because for reviews of LCA results, we realized that there are a lot out there that discuss these comparisons between the different and the break-even points. But our work here is more focused on the method part. It's about how people obtain this results, and does it all make sense actually? Should we believe all these numbers? Because these numbers come from decisions made by the LCA practitioner, right? So we really didn't dive into the results, but I can give you some insights about the technology itself, if you wanna know more about it. From my readings at least, and this is not about this paper specifically, I think that the electricity modeling topic is the top thing, because if you read all the papers when it compares the EVs, even not only the EVs, the zero emission vehicles in general, including hydrogen, it's all about how you generate this electricity and how you feed your manufacturing process and how you feed your use phase, because the cleaner this gives a huge advances to EVs. But it's not always the case that EVs are better. And this is why LCA is very important, because blind decisions can really lead to bigger problems in other, think of batteries and the manufacturing and the raw material needed.
Yeah, and your work was mainly focused on making sure that if you have different LCAs, that you can compare the results of those LCAs. And I'm sorry that I need to interrupt this discussion, but I need to do some quite strict timekeeping at these meetings, and we are hitting 11 o'clock. So Hazem, thank you once again for your presentation, and thank you all for your participation. I hope to see you at the next Circular Industry Talks in 2 weeks' time with Flora Poppelaars from the design agency Partners for Innovation, who will talk about e-waste collection in relation to consumer behavior. Have a nice day.
Thank you so much. Thank you for the invitation. Thank you all for listening. Bye.
Thanks. Bye.
Thanks, Hazem.
Bye.
Thanks a lot, Elise. Thanks all. Bye.